So learning target 8 says I can write an equation from a given polynomial graph. So for this learning target, I'll give you a graph and you need to write an equation for it. Now, sort of towards the beginning of this content, we didn't know how to find the exact leading coefficient for our equation, so we were just sort of being like, well, I know it needs to be positive, so I'm just going to pick any positive number to put in there. But we did at the very end learn to use the equation and an extra point on the graph to actually solve for the exact leading coefficient. So now that we know how to do that, we want to actually solve for the exact leading coefficient. So that's what this part of the direction means. Remember to use a point on the graph to solve for the exact leading coefficient. So the first thing that I like to do is I like to identify where my x-intercepts are and just make myself a little chart listing the x-intercepts, the appearance of the graph, and therefore what the multiplicity needs to be. So let's see, looking at my graph, I can see that I have an x-intercept at -3, -2, and 1. So I'm going to list those out. -3, -2, and 1. And then I'm just going to sketch myself a quick little picture about what the x-intercepts look like, what the graph looks like near the x-intercepts. So near x equals -3, if you notice it's sort of like passing straight through. Near x equals -2, it's sort of touching and turning back around. And then the same thing is happening at x equals 1. We're sort of touching and turning back around. Now, based on the appearance, that tells us what the multiplicity should be. When we pass straight through, that is a multiplicity of 1. When we touch and turn back around, that's going to be a multiplicity that is even. Now, we don't know for sure by looking at it whether something is going to be an even multiplicity in 2 versus an even multiplicity in 4. So I typically choose sort of the lowest possible multiplicity that it would be. It makes our algebra a lot nicer later on. So I'm just going to say that each of these even multiplicities, I'm just going to call them 2. If you wanted to call them 4 or 6 or 8 or whatever, go for it. It'll just make the algebra a little bit uglier. Okay. Let's see. So now maybe let's take that information and sort of start to put it into an equation. Now, if I know that I have an x-intercept of -3, that means that I need to have had a factor of x plus 3 in my equation. If I have an x-intercept of -2, that means I must have had an x plus 2 in my equation. And if I have an x-intercept of 1, that means I must have had a factor of x minus 1 in my equation. However, these factors could have multiplicities on them. They could have exponents on them. And to figure out what the exponents should be, I need to look at my multiplicities. So this x-intercept, -3, has a multiplicity of 1, so there should just be an exponent of 1 on that factor x plus 3. The factor x plus 2, that gave us our x-intercept -2, and we know that that x-intercept has a multiplicity of 2, so this factor better have an exponent of 2 on it. And our x-intercept 1, that had a multiplicity of 2, so on the factor x minus 1, that better have an exponent of 2 on it. Now, looking at the graph, we should be able to at least determine whether the leading coefficient is positive or negative. So if you notice, the end behavior of the graph goes down to the left and up to the right. that sort of end behavior comes from having an odd degree and a positive leading coefficient. So we know that our leading coefficient is some positive number, but we don't know exactly what it is yet. So our strategy in class was we would put a little leading coefficient in front of our equation, and we would use another point on the graph to solve for that leading coefficient. So let's turn to our graph and see if we see a nice point. So it looks like the y-intercept right here, it looks like that happens at 0, 6. So this is 10, which means each little box is 2, so this would be 2, 4, 6. So it looks like there's a nice point on the graph, 0, 6. So we could use that point to solve for our leading coefficient A. Now remember, the whole idea behind an equation is that it's supposed to describe the relationship between x and y for any point on the graph. So in particular, if I plug in 0 for the x and 6 for the y, I better have a true equation, so then I'll be able to solve it for A. So let's do that. Let's put in 6 as my y value. And let's put in 0 as my x value. And now I just have a nice equation that I'm going to be able to solve for A. So this involves a bit of algebra. So let's go inside each of our sets of parentheses and let's simplify as much as we can. So we have 6 equals A times 3 times 2 squared times negative 1 squared. Now let's simplify where we have exponents. So 2 squared is 4 and negative 1 squared is 1. Now we can keep simplifying this right-hand side a bit. 3 times 4 times 1 is 12, so we just have 6 is equal to A times 12. And all we need to do now to solve for A is just divide both sides by 12. So I get that A is 6 over 12, or 1/2. Now I'm not quite done yet because remember my ultimate goal was to come up with an equation. So this algebra here was just figuring out the A value of the equation, or the leading coefficient. So at the end I need to go back and plug that A value in where it was supposed to go in the equation in the first place. And this is going to be my final answer. So let's try one more example like this. Again, we're first going to identify what our x-intercepts are. We're also going to sketch sort of what the appearance of the graph is like. And that's going to give us information about the multiplicity. So looking at our graph, we see that we have an x-intercept at -3. And at -3, it looks like the graph is just sort of going straight through the x-axis. Next, we see that we have an x-intercept at -1. And at -1, it looks like our graph is making that, what we call the awkward S shape near there. And then finally we see we have an x-intercept of 2, and the appearance of the graph there is that it's sort of touching and turning back around. So we want to use the appearance of the graph to identify the multiplicity of each of the x-intercepts. So we know that when our graph crosses straight through, that means our x-intercept has a multiplicity of 1. When it makes this weird little curvy S shape, that's when our x-intercept has a multiplicity that is odd and greater than 1. And when our graph sort of touches and turns back around and doesn't go through the x-axis, that's when we have an even multiplicity. So let's pick 2. So we can sort of get started setting up our equation. If -3 is an x-intercept, then x plus 3 needs to be a factor. If -1 is an x-intercept, then x plus 1 needs to be a factor. And if 2 is an x-intercept, then x minus 2 needs to be a factor. And then we can just use our multiplicities to fill in what our exponents should be. So we should have a 1 on the exponent, we should have a 1 as an exponent on the factor for x plus 3. We should have a 3 on the factor x plus 1. And we should have a 2 on the factor x minus 2. Now, we can figure out by looking at our graph whether our leading coefficient should be positive or negative. So notice that our graph is going up in both directions, which means that our polynomial will have even degree. And if it's going up in both directions, that means that it's even degree and it has a positive leading coefficient. So we know that this is going to have a positive leading coefficient, but we don't know exactly what it is yet. So what we have to do is we have to algebraically solve for our leading coefficient. And we're just going to call it A. Now to solve for our leading coefficient, we need to find some other nice point on the graph. So looking at this graph, it looks like our y-intercept is at 3. So the point 0, 3 seems to be on the graph. So let's use that point. So this equation that we're creating, it's supposed to be true for any point x, y on the graph. So in particular, it should be true for the point 0, 3. So let's plug in 3 for y and 0 for x, and that should give us a true equation. So 3 is equal to a times 0 plus 3 times 0 plus 1 cubed times 0 minus 2 squared. And this should be a true equation that we can solve for a. So again, let's simplify inside the parentheses first. 0 plus 3 is 3, 0 plus 1 is 1, and 0 minus 2 is negative 2. Let's next simplify our exponents. 1 cubed is 1, negative 2 squared is 4. So again, 3 times 1 times 4 will just be equal to 12. And to solve for a, all I have to do is divide by 12 on both sides. So I get that a equals 3 over 12, which is the same as 1 over 4. Now again, I'm not quite done. The purpose of this was to find the leading coefficient of my equation, but I still need to give a full equation as my final answer. So what I'm going to do is just sort of go back and put this leading coefficient into my original equation that I had. And let me just double check that I got the exponents correct. Yeah. So this is going to be my final answer, is this full equation down here.